Let's complete our JiTickLogic's base node types and get done with it. Hello everyone, this is Ali Reza. Welcome to the Mentor Code Lab. The only nodes that are remaining are things that normally you wouldn't use in Minecraft. The reason is that they do things in a random fashion. For example, the next node that I don't have inside application list to show you is a random node. Now, assuming that instead of parallel, we have a random node here, a random node will choose only one node from its list randomly and tick it and send back the result. So I'm not sure in this tick which one of these three action nodes that we have here will be ticked. It can be the first one, the middle one, or the left one, or the right one. I don't know. In the next tick, again, we are not sure. So the chances are that we may tick one single node, maybe the middle one, 2 times or 3 times before ticking another one, and it's totally random. Because of this randomness, I'm not sure if there is any room for any logic inside Minecraft to do things like this, unless you want to use this thing inside an entity AI, like a mob. That time, yes, having random behaviors may help, especially if you want a very complex triple A artificial intelligence for your AI. Anyway, I will add it because it's not a big deal. So I will add a random node. As always, it will implement the node, and no, it will not implement the children and not implement the I running node manager. Actually, why not? Let's have it. So if you take note, so far, only the action node and condition node didn't have this implementation. So not node is registering itself, parallel node is registering itself, repeat node is registering itself, selector, sequence, start node is not, until failure, and until success. So most of these are actually registering themselves as the busy one and not the children, because they need to do things in fashion. So here we will have to implement our JiTickLogic, and believe it or not, we don't need any parameters, so I will just add the constructors as they are, and here I will call super as it is. Everything will happen in JiTickLogic. So here we want to choose a random child. We say if, actually, let's do a copy paste because it may make my life easier. So if we don't have any children, it's wrong, just error out. Otherwise, we say int random index equals to random next int of the children.size. Okay, so random returns a number between 0 and 1. Instead of this, actually, we can call random. Let me see. Do we have next int random? No. Okay. So this returns some number between 0 and 1. And if I want to look, we don't have any overloads for this, do we? No, round, random, and add extract. So if we want to read the document, it returns a double between 0 and 1. And returned values are blah. So if we want, we can use this. x1 multiplied by 1 minus random plus x2 multiplied by that. I don't care about that. Problem is that it's 1 above of what we want. So if we have 10 members, the topmost will be 9th, and we need to reduce 1 from our size and then multiply it to random. So what we get here is a number between 0 and 9, for example, because the random is returning from 0 to 1, and 1 means the last child, 0 means the first child. Okay, now that we have that, we want to handle the running state. So we say tick status, get the child at that random index and tick it. If the status is equal to running, we want to say tree.add running this and then return the running state. Otherwise, we want to return the status, whatever it is, we don't care. It's success, it's failure, it's errored. We just want to return that. And that is our random class. Now we have 2 extensions, one for the sequence and one for the selector. So I will say Java class random sequence. And again, this is it. So if we look at the sequence node, I can convert it from while loop into a for loop. Let's do it here. And this will be another implementation here, so we don't need to worry about things. Okay, first we want our constructors. All we are doing here we call super. Now in JiTickLogic, we will say list of node t, and we call it shuffled children equals to new array list. Then we say collections dot shuffle the shuffled children with a random number. Now we don't have that. And as you see, it asks for random. So we can say new random from Java util. Okay, and I'm not producing any seed. If you produce a seed, the result will always be the same. We don't want that. Okay, actually, I can assign it here. So this is coming from here. We say random equals to new random, and this will be a private final, and I will use it here. So each time we are ticking, we are using the same thing. So it's a little bit optimized now. So we say for node t child inside our shuffled, we want to do things. So let's go into sequence node, and we bypass that one. We want this part. We don't need that. We are not caring about this. So we say that if we are failed, we return failure. If we are running, then we assign ourselves to be running and then return running. At the end of the loop, we return success. And that's our random sequence node. The next one is actually random selector, and that's almost identical to selector. Let's take a look. Random selector node. Let's close this guy, get that part, add it here. So again, we want a private static final rand equals to random from Java utils. Then let me get this copied, and I will add the constructors first. This one called super, and paste it here, and we will take a look at the difference. We are shuffling our children, we are looping through our children. The only thing is that if we are success, we immediately break out and succeed. If we are running, we return running. Otherwise, we fail out. As simple as that. We have covered our random sequence and random selector, and this guy needs to be random sequence node. Anyway, let's take a look at our list. Of course, I don't have random here. I will add it. So we covered random selector and random sequence. If we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That will be random. The only thing remaining is sub3. And let me take a look at my nodes and see how bad it can be. Actually, it's not. So let's add it and get done with it. So let's have our sub3 node. Now sub3 node is again gonna manage itself. Here we want a private behavior, or here, what did I call it? Logic tree of type T, and we call it sub3. Now we want our constructors, both of them that accepts the sub3. Here I will call the super first. So we call the super and we add the sub3. Finally, we have our tick logic. Inside tick, we say if sub3 equals null, we return error. We should have a sub3. And I'm not going to throw illegal exceptions. I could do that, but the whole purpose of returning error is that your block entity can handle that. Tick status equals to sub3.tick, and we say if the status equals to running, we want to say tree.add this, and finally return the status. Funny enough, this is a sub3. However, we need to override the reset method, I think, because we established the fact anytime you have an attribute somewhere, you need to assign that attribute, and I think we can make it final. We don't want to set the sub3 on the fly. So we say if sub3 does not equal null, sub3.reset. We need to check null here. We can't error out because we are not returning anything here. So if the sub3 is not null, then reset it. And that's it. We finally made our whole solution ready for what we need inside Minecraft. Now, from now on, inside our logic package, we can add things that are dedicated to Minecraft itself. For example, we can check if we have energy, or if we should use energy, or get the energy amount. I don't know, reduce the energy and things like that. And that would be it. It's a long list actually, and it will go on and on. And remember, right now our library for the energy, the fluid, doesn't provide anything related to JiTickLogic as we have for the fields on the property. But we can add them if we want to, and we need to add them so that our JiTickLogic can read the block entity and get suppliers, for example, for the process or energy amount or energy capacity, fluid amount, fluid capacity, anything that we need to handle there. Even the consumers for setting the energy amount or setting the progress, or I don't know, anything else, because that is how things should progress forward from now on. Anyway, right now you have a complete solution for a behavior tree. It's bulletproof, it's really solid, and can handle any complex logic as you want. And no matter how much I think about it, the standard behavior tree system doesn't have any node that we missed. We have few tweaks here and there because, as I said, the parallel is not multi-threaded. We are handling multiple running nodes at the same time. But, one thing that I need to fix, and I'm not fixing it right now, is that at any time if we are running a node and that node returns success, we are sending it back upward, but we are not going for the next child there. We assume that our start node will handle itself, okay? But here, for example, this tree is totally wrong, by the way. A start node has only one child, not multiple. Anyway, the way we implemented it right now, it will go for sequence and then selector, so it's okay. But in the concept of a behavior tree, it's totally wrong. A start node should have only one type of a composite, being sequence or a selector or parallel, whatever it is. So we need to handle that or sit back and think. Basically, what we have on the start node right now is somewhat close to parallel, but we don't count for anything else. Anyway, this is a little bit different from the normal behavior tree, and I need to do a brainstorming on another video about this whole thing, and we'll talk about it in the next video. If you like these videos, please subscribe to the channel, hit the like button, and turn on that bell so that when I publish a new video, you will get informed. Have fun, everyone. Bye.